Welcome to MMA, your Mixed Model Academy.
In this tutorial, we're going to learn how to create a mixed effects model in MMA. This tutorial follows on from the How to Create a Project in MMA tutorial, where we created an MMA project to analyze data from a clinical trial with repeated measurements. The trial compared 3 drug treatments, A, B and C, for controlling hypertension. Patients from 29 medical centres participated in the trial, and their diastolic blood pressure was recorded at 6 visits, 2 pre-treatment and 4 post-treatment. The post-treatment diastolic blood pressure measurements are in column DBP, with the visit column indicating which post-treatment visit, numbered 3, 4, 5 or 6, the measurement was taken at. Column DBP1 contains the average diastolic blood pressure from the 2 pre-treatment visits. If you're following along in MMA, you can download the data from the Multi-Centre Hypertension Trial project. You can find out more about this dataset and its analysis in Brown and Prescott's book, Applied Mixed Models in Medicine. Let's create a model. Clicking on the Create New Model button opens a page where we can define our mixed effects model. The variables in our dataset are displayed on the left-hand side. You can preview the dataset and, if needed, change variable types. We'll use the form on the right to define our model. The aim of the clinical trial was to assess the effect of the 3 drug treatments on post-treatment diastolic blood pressure, variate DBP. Therefore, DBP is the response. Click in the response field and select DBP from the drop-down list. As a patient's post-treatment blood pressure measurements are likely to be affected by their initial conditions, we'll include the pre-treatment measurement DBP1 as a covariate in the fixed model to control for pre-treatment differences between patients. Click in the fixed model field and select DBP1 from the drop-down list. Our fixed model must include treat, the drug treatment factor which we're interested in studying. To add a main effect for drug treatment, select the plus operator and then select treat. The following operators can be used in a fixed model formula. We'll allow for an underlying change in DBP over the 4 post-treatment visits by including the visit factor in the fixed model. Finally, as the drug treatment effects may differ between visits, we'll also include the treatment by visit interaction. The dot operator is used in this case to specify an interaction.
Since both the main effects of treat and visit have been included, treat.visit corresponds to an interaction. Otherwise, it would represent a nested effect.
Recall that the patients were recruited from a sample of 29 different medical centres. It's important that we account for this structure in our model. We can do this by including the centre factor as a random term. Note, including centre as a random rather than a fixed term enables us to make inferences about the wider population of medical centres, not just the 29 we observed.
The general definition of fixed and random terms is shown here.
Using the form, we can define very complex random models. We can include multiple random terms, specify a simple or complex variant structure for each random term if we need to, and create nested, heterogeneous, and joint random terms. You can learn more about specifying random and residual models in our video tutorial defining complex random structures in MMA. In our model, we'll include only a single uncorrelated random term, center.
As patient diastolic blood pressure was recorded at 4 visits post-treatment, this is an example of a repeated measures dataset. Therefore, we need to take into account the correlated nature of measurements taken on the same patient over time. This is done by specifying a correlation model for the residual. In this case, diastolic blood pressure measurements taken on the same patient at consecutive visits should be correlated, but measurements across patients are independent.
The residual for this data set is equivalent to the patient by visit interaction.
The random term corresponding to the observational unit is equivalent to the residual. As our aim is to model the correlation between diastolic blood pressure measurements taken on the same patient over time, we need to set the variance model associated with the patient term to ID, and select a correlation model for the visit term.
MMA offers several choices of correlation model. AR1, an autoregressive model of order 1, which allows the correlation between measurements to decrease as the time between visits increases. CORE, a simple correlation model, which assumes that the correlation between measurements are constant over time. CORG, a general correlation model, which allows a separate correlation for every pair of visits. ID, the identity model, which assumes the measurements taken on the same patient are independent of one another. A plausible model for many repeated measures datasets with equally spaced time points, such as ours, is the autoregressive order 1 model, so we'll select AR1. That is, for our model's residual structure, we are saying that the residuals between different patients are independent, but residuals originating from measurements from the same patient at different time points will be correlated based on an AR1 variant structure. Finally, we need to give our model a name. Now that our model is completely defined in terms of the fixed and random models and the residual structure, we are ready to click Generate to produce ASREML R4, RNLME, and SAS syntax for our model.
Thanks for watching.
Join us for the next video in this series, Fitting Your Model in ASREML R4, where we use code generated by MMA to fit a mixed effects model in ASREML R4 and produce useful output.